The second periodic trend that we're going to discuss in class is that of ionization energy. Ionization energy is the energy needed to remove an electron from an atom. It's one of our vocab words. And as you go through that, think about it this way. If something is hard to do, it takes a lot of energy, high energy. If something is easy to do, it takes not very much energy, low ionization energy. So if it is easy to remove an electron from an atom, then it would be low ionization energy. Easy to do, it's low. Hard to do, it's high. And people sometimes confuse those, but it's not too bad. So let's talk about what we're dealing with here. So let's look at a couple of representative elements. Let's look at chlorine. Chlorine has how many valence electrons? 7. It has 7. It has 17 total, but 7 valence electrons. And it wants to have how many valence electrons? 8, because of the Elizabeth. Faster. Because of the octet rule. Which rule there? Sean, who didn't ring in fast enough last night? Okay. Were you in, Sean? Never mind. So it wants 8, so it needs one more. So if you need one more electron, and I come and try to take one away from you, what do you say? You say no. Then I say, give it to me anyway, and then I start wrestling for it from you. Is that going to be easier to do or hard to do? Hard to do. So chlorine, it might depend on who it is, but chlorine's very strong. So chlorine has a very, would you say, high or low ionization energy? High ionization energy. So if I try to take an electron away from chlorine, it's going to be very difficult to do. Now let's take a different example. Let's talk about potassium. Potassium is way over there on the left. It has how many valence electrons? It has 1 valence electron. And what does it want to do with that valence electron? It wants to get rid of it. Wants to get rid of it. So if I come and try to take that away from potassium, is it going to fight me? No. So is it easy or hard? Easy. High or low? Low ionization energy. So we're talking about ionization energy. We see now that potassium is low, chlorine is high. So what we're going to do then is we're going to look at the trend. What is the trend? As you go left to right on the periodic table, what is the trend on ionization energy? It gets stronger, gets higher, it's harder. Exactly. So the trend on ionization energy is that it's harder, or it increases as you go left to right across a period. And that's fairly obvious. When you get to noble gases, it's really hard to take away their valence electrons. So now let's, that's one trend. That's a trend as you go left to right. Now let's talk about what happens as you go up and down. And this one's a little bit more nuanced. This one's a little bit harder, so we have to talk about it for a little bit longer. So let's take two representative examples. Let's take the example of two things in the same group. Let's say, so we can go to sodium and rubidium. Okay, sodium and rubidium. We'll look at those two. Now they both have 1 valence electron, so they both want to give it away. So you'd say, well, it's equally easy to take from either, right? But that's not exactly true, and we'll have to look at this and see what we mean when we say it's not exactly true. We if we go ahead and draw it, oh, that's the one that's already done. I need to start over. Let's do sodium. Sodium has how many protons? That's right, 11. And so if we wanted to kind of model its protons, you have a plus sign to show its protons. And its electrons are, we'll represent those by this green electron cloud circle. And then I'm going to put the outermost electron, the one that we're going to try to steal, the one we're going to try to take away, we're going to put that out there. And then for rubidium, how many electrons total does rubidium have? Not valence electrons, but total. 37. 37 protons, therefore 37 electrons. So if I were going to model the plus after how many protons it has, what should I make this plus? Bigger. There's a lot more. There's 37 of them, okay? And what about the size of the electron cloud? Should be a lot bigger, shouldn't it? Because this is in the it's filling a 1, 2, 3, 4, 5s, whereas sodium is filling a 3s. In case you're wondering why those are different, the 3s orbitals are smaller than the 5s orbitals. So let's stick that electron on there. Now let's see which one's easier to steal. Who thinks that it's going to be easier to take from sodium? About half the hands go up. Who thinks it's going to be easier to take from rubidium? About a third of the hands go up. Now raise your hand if you haven't raised your hand yet. Several people who just raised their hands, and a few that didn't. So there we go. So let's figure this out. So the argument for rubidium is pretty easy. Why would you think that this electron here on rubidium would be easier to take away? Okay, it's got more space to try to defend. That's right. That's one way to think about it. And so it's kind of farther away, so you'd think it might be easier to pull it off, right? Because the basic interaction here is between the outer electron and the nucleus. They're positive, they're negative, they attract. And so that's why it's pulling it in. And this guy is pulling his in, and it's real. You look at that and you say, well, it's a lot easier for sodium to pull it in because it's closer, whereas this one's really far away and it's going to be harder to hold on to. And so that's an argument for why rubidium would be easier to steal from. What's an argument for why sodium would be easier to steal from? Well, they both want to lose one electron, though, so that doesn't help. The guess was that because it wanted to lose one, but rubidium also wants to lose one, so that's not going to help us break the tie. What I want you to look at is the blue things. That's 11 protons. What's this? That's 37 protons. Now, which one of them should be better at holding the electron in, 11 or 37? 37. 37 is a lot stronger nuclear pull. So the 37 should win, right? But the reason that we're not sure if it does is because it's got a pull from a lot farther away. So we get into a little trouble. We're not sure who's going to be better at pulling the electron in, and so we actually need to find a tiebreaker. And here's the tiebreaker. What we haven't talked about yet are, we talk about this electron, but aren't there 36 other electrons between the nucleus and that outermost electron? And so I'm going to try to draw those as this big green cloud. How many are there here on this guy? It's going to be 10, that's right, and so we put that in there. And so here's what I want you to realize. When the nucleus tries to hold on to that electron, it's trying to hold on, trying to pull it in, it's got to reach through 36 electrons that are in its way. This guy, he's weaker, but it's closer, but he's only got to reach through 10. And those inner core electrons, they shield the outer electron from the nucleus. We call this the shielding effect. The shielding effect. So in other words, as this nucleus tries to pull this electron, these core those core electrons get in the way. And so does this, but there's not as many core electrons getting away, so this gets shielded more than that. Rubidium gets shielded more than sodium. Therefore, it actually is easier to come and plop that guy off than that guy. So the shielding effect, it says that it is easier to take an electron from a large atom. It's easier to take an electron from a large atom because all those inner core electrons getting in the way. So if we go back to our periodic table, what's our trend? For ionization energy, as you go left to right, it gets, what did we say earlier? Bigger, stronger, harder to take away. And as you go down, they get these bigger atoms down at the bottom are easier to rob, right? So the trend here is it gets smaller. So there's your ionization energy trend. One last thing that we need to talk about before we cut this off is we need to talk about electron affinity. Woo! Woo! There it is. Electron affinity. Electron affinity is not quite the same thing as ionization energy, but it is related, as we'll see in a moment. Electron affinity measures how easy it is to bring an electron in. How easy it is to bring an electron in. Recall that we just talked about ionization energy. We learned that for ionization energy, it measures how hard it is to take one out. This measures how easy it is to put one in. You think they're related a little bit? If someone has one valence electron and it wants to get rid of it, is it going to be easy to give him an electron? If you have something burning a hole in your pocket, you want to get rid of it. Is somebody wants to give you another one of those things you're trying to get rid of? Is that something you want? Are you going to accept it? No, you're not going to accept it. And so it's hard. You have low affinity for the thing you're trying to get rid of. Whereas if it's something you're holding on to, you're more likely to want another one. So the idea is that electron affinity is kind of very closely related to ionization energy. They both kind of go together. If it's harder to take, it's also easier to give, and if it's easier to take, it's probably going to be harder to give. And so what we find is that the trend in electron affinity is exactly the same as ionization energy. It decreases as you go down the periodic table, and it increases as you go to the right on the periodic table. And that, there we go, now you can see it. Decreases as you go down, increases as you go to the right, and that's the final trend.